Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, I would like to talk about the posterior predictive distribution in the normal model. So, first, let me show you one way of doing things, which is the way that we have used to obtain our posterior predictive distributions in the past. We used the approach that I am about to show you for data with binomial likelihood, and we did the same for data with Poisson likelihood. Okay, so the idea would be this. We have a sample of size n. We have already observed that, and now we would like to come up with the predictive density, the posterior predictive distribution for the next observation. Okay, so the way we did it in the past was using calc, like in this case, right? We have our posterior distribution, we have the likelihood of the next observation, and then we integrate with respect to mu, and that is going to yield the posterior predictive distribution. So in the case of a normal likelihood, if you're considering either a flat prior or a normal prior, you know that the posterior is going to be normal. Then this here, the likelihood, is also going to be normal. So that integral that you have to solve is very similar to the one we had to work on to obtain the updating rules. Okay, so it would be the same kind of procedure again as the one that you would do to obtain again the updating rules. Okay, so in this case, right, in the case of the posterior predictive distribution, it turns out that the posterior predictive distribution is going to be normal with mean mn, where this guy represents the posterior mean after observing n observations, and the variance happens to be the sum of sigma squared and the posterior variance after observing n observations. Make sense? Okay, so as I said, we did this before to obtain, we did something like this before to obtain the updating rules. Let me give you an alternative approach. So let's refer to the next observation as y sub n plus 1. Okay, so this guy represents the next observation. Now this guy, our next observation, has a normal distribution, right? It comes from a normal with an unknown mean mu. That's our parameter of interest, and sigma squared. And remember that our assumption at this point is that sigma squared is known. Is known. Okay. Now note that we could think about that next observation like this, as a sum of mu plus epsilon, where epsilon has a normal distribution. Epsilon has a normal distribution with mean 0 and variance sigma squared. Right? So it's another way of thinking about the next observation. Mu plus epsilon. Epsilon has a normal distribution with mean 0 and variance sigma squared. So that would yield this, right? A normal with mean mu and variance sigma squared. Okay? But now, a few observations. Note that the distribution of epsilon doesn't depend on mu, and therefore epsilon and mu are independent. Okay? So just note epsilon and mu are independent. Again, note that the distribution of epsilon doesn't depend on mu, so epsilon and mu are independent. Okay, now assume that mu, that parameter, is updating. It's updated after we have observed a sample of size n. Okay, so let's write that down. Assume now that the updated distribution of mu and what I mean by updated is after the observation of a sample of size n. So assume that distribution is normal. Okay, and let me use the same notation that they used for the parameters. Mn, I'm going to be using Mn for the mean, the posterior mean after observing n observations, and S sub n squared for the variance. Okay, there we are. Okay, so if that's the case, right, if mu after observing your sample of size n has that distribution, then yn plus 1, the next observation, is a sum of two normal random variables. Therefore, the distribution of the next observation is going to be normal, and the mean of that normal is going to be the sum of the means of these two random variables. Okay, then the mean is going to be 0 plus mn, so mn in the end, and the variance is going to be the sum of the variances, because we have a sum of two independent normal random variables. The sum, well, the variance of a sum is the sum of variances if the random variables are independent. And that would be, this is given that you have already observed. This is the one after updating, right, mu with the information coming from that sample of size n, right? So this would be the posterior predictive distribution, and I'm using that notation to refer to the distribution of yn plus 1 given that you have observed a sample of size n. Let me write it down like this. Y1, Y2, up to yn. Okay, and now if we compare to what we have here using basically the definition of the posterior predictive distribution, right, which would be the likelihood of the next observation times the posterior of mu, in this case after observing the first n observations, right? They ended up with normal mean mn, that is the posterior after observing n observations, and then the new variance for the predictive posterior distribution, the sum of sigma squared, and the posterior variance after observing n observations. So, as you can see, this idea of expressing the next observation as mean mu plus epsilon, right, where this guy is just normal with mean 0 and variance sigma squared, right, was helpful to quickly find that posterior predictive distribution. Okay, we have the same result here. Okay, so let's summarize what we talked about here. We know that there are two different ways of finding the posterior predictive distribution. One would be this, basically using the definition. That's the way we have done things. For the other likelihoods, we have dealt with binomial and Poisson likelihoods, right? We could do the same here for normal likelihood, but we know that it's going to take time, and the kind of math that we have to do would be similar to what we did when we obtained the updating rules. Okay, so this is just an alternative approach, and one that yields the same result much faster. Okay, so bottom line, the posterior predictive distribution of a normal likelihood when you are using a normal prior from u or a flat prior from u will be normal with parameters mn, where this guy represents the mean of a normal after the mn represents the posterior mean after observing n observations, and then the variance includes sigma squared, that variance for the likelihood that you assume known, plus the posterior variance after observing your n observations. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. Bye.